Okay, in this lecture, we will discuss Taylor and Maclaurin series Kreyszig problem solving session. And this is lecture 8 of this module. Okay, this is the last section of module 4. So in this module, in this lecture, we will discuss Taylor series and Maclaurin series, and we will discuss Kreyszig exercise problems. Now, uh, so, now let us recall what is Taylor series. Taylor series. So Taylor series of f of z at z equal to z naught. A point is given by sigma. Sorry, f of z is equal to sigma n equal to 0 to infinity f nth derivative at z naught divided by n factorial into z minus z naught all power n. Now, Maclaurin series is when is a special case of Taylor series when z naught is equal to 0. So, Maclaurin series of f of z is equal to sigma n equal to 0 to infinity f nth derivative of 0 divided by n factorial into z power n. Okay, so now we will discuss few problems. So first we will do problem number 1. Find Maclaurin series and its radius of convergence. Radius of convergence is not in your syllabus. അങ്ങനെ question വരാറില്ല. But we need to find Maclaurin series. Okay. So I will show how to find out radius of convergence also. Okay. So first question, we have to find Maclaurin series of f of z is equal to sin 2z square. Okay. So we already know. So for this, one method is we have to find out f dash of 0, f double dash of 0, etc. That is f of 0, f dash of 0, f double dash of 0, etc. And we will substitute in this formula. Or other easier method is if we already know the Taylor series, the Maclaurin series expansion of sin z, then we can easily substitute 2z square instead of z. So this is so we already know Maclaurin series expansion of sin z. Okay, what is Maclaurin series expansion of sin z? Z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial plus etc. So this we already know. Now, in order to find Taylor's, then Maclaurin series of sin 2z square. So this can be written as sin 2z square is sin root 2z all square. So therefore, sin root 2z all square is equal to, now we already know that Taylor's Maclaurin series expansion of sin z. So now here instead of we replace okay, this I am calling equation number. Replace z by root 2z in equation number 1. So if we replace this, then what you will get, root 2 root 2z square, sorry, the root 2z all square minus root 2z all square all cube divided by 3 factorial plus root 2z all square all raised to 5 by 5 factorial minus etc. So this will be the uh, Maclaurin series of sin 2z square, that is sin 2z square. Okay. Now if you write it in the form n equal to n equal to 0 to infinity, 0 to infinity, this you can written as root 2z all square all raised to 2n plus 1 divided by 2n plus 1 factorial, and there is a when n equal to 0 plus n equal to 1 minus plus minus. So this is the uh, Maclaurin series of sin 2z square. Okay. Now if you want to find out uh, next next problem, so this is very easy, right? What we have to do is we already know that Maclaurin series of sin z. Then we just replace z by root 2 z all square. Okay. Now I will do this problem, fifth problem. F of z equal to 1 by 2 plus z raised to 4. 1 by f of z is equal to 1 by 2 plus z raised to 4. So find Maclaurin series of f of z is equal to 1 by 2 z raised to 4. Now, now so we know this is of the form 1 by 2 plus z raised to 4. So we know Maclaurin series expansion of 1 by 1 plus z, right? What is 1 by 1 plus z? Maclaurin series expansion is 1 minus z plus z square minus z cube plus z raised to 4 minus etc. So you have to know this, okay, so that we can do. Now we have to change this in this format. So you can write now 1 by 2 plus z raised to 4, you can write it as 1 by 2 into 1 by 1 plus z raised to 4 by, and okay, this is valid when mod z less than 1. Okay, so this is valid. We already find the radius of convergence mod z less than. Then this is equal to 1 by 2 into, okay, so this is something of the form 1 by 1 plus z, right? This is something of the form 1 by 1 plus z. So instead of z we have now replace z by z raised to 4 by 2. So this 1 by 1 plus z raised to 4 by 2 is equal to 1 by 2 times. Now we will expand by this. Instead of z, there is z raised to 4 by 2. So 1 minus z raised to 4 by 2 plus z raised to 4 by 2 all square plus minus z raised to 4 by 2 all cube plus etc. And this is valid. This is valid. This is valid when mod z instead of z, z raised to 4 by 2 less than 1. So that means it implies mod z raised to 4 less than 2. So which implies if you take fourth root, mod z minus 0 less than 2 raised to 1 by 4. Okay. So this is that means 1 by 2 plus z raised to 4 equal to 1 by 2 times 1 minus z raised to 4 by 2 plus this can be written as z raised to 8 by 2 minus z raised to 12, sorry, 2 square, 2 square, z raised to 12 by 2 cube plus etc. And this is valid when mod z less than 2 raised to 1 by 4. So here radius of convergence is 2 raised to 1 by 4. Similarly, here also you can find radius of convergence. Okay. So this is equal to sigma n equal to 0 to infinity minus 1 all raised to root 2 z. Okay, root 2 z all raised to, this can be written as 4n plus 2 divided by 2n plus 1 factorial. Now if you find like ratio, just limit this root 2 z all raised to 4 2n plus. So we know that, okay, so, so we know that how to find radius of convergence. So I will give you an idea. I am not using the formula, I am just giving an idea. So we know that an sigma, okay, sigma n equal to 0 to infinity cn, this series converges if by I am using ratio test. You already studied it in calculus. If limit n tends to infinity, cn plus 1 by cn modulus this is less than 1. And what we will do is so 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 here in the above, what is cn? Cn is so our series is sigma sin 2z square is sigma minus 1 power n equal to 0 to infinity root 2z all raised to 4n plus 2 divided by 2n plus 1 factorial. So here Cn is equal to minus 1 power n root 2z all raised to 2n, sorry, 4n plus 2 divided by 2n plus 1 factorial. Now we will find this. Okay. So this converges if limit n tends to infinity minus 1 power n modulus of cn plus 1. So root 2 z all raised to 4n plus 1 plus 2 divided by 2n plus 1 factorial. 2n plus 1 plus 1 factorial all divided by minus 1 power n root 2 z all raised to 4n plus 2 divided by 2n plus 1 factorial. So this is less than 1. By simplifying this, you will get you will get mod z minus 0 less than infinity. So if you simplify this, you will get this. So here radius of convergence is infinity. I am not doing this simplification. If you find this limit and apply this, then you will get mod z less than. So radius of convergence. So it's not very important for your examination, but very important for uh, competitive examination. Okay. If you have any doubt, you can ask me. Otherwise, we can move to next problem. Okay. So now I will do this problem. If you have some confusion for this one, find this is on in the integral. So what we will do is find Maclaurin series of so find Maclaurin series of integral 0 to z e raised to exponential of, that means e raised to minus t square dt. So we want to find out the Maclaurin series of this integral. So the one of the thing is we cannot integrate. One method is first integrate and then find series. Okay, but we cannot integrate this. But for a power series or Maclaurin series, it's enough. അതായത് നമ്മൾ ഇത് ഇൻ്റഗ്രേറ്റ് ചെയ്തിട്ട് സീരീസ് കണ്ടുപിടിച്ചിട്ട് ഇൻ്റഗ്രേറ്റ് ചെയ്യുന്നത് both are same. So that is an important property. So what we will do is, we already know what is Maclaurin series of e raised to z. So what is Maclaurin series of e raised to z? 1 plus z by 1 factorial plus z square by 2 factorial plus etc. Z power n by n factorial plus etc. Which implies e raised to minus z square or t square. Then what is Maclaurin series of e raised to minus t square? Instead of z, I am putting t square. So 1 plus minus t square by 1 factorial plus minus t square all square by 2 factorial plus etc. So this you will get 1 minus t square by 1 factorial plus t square all square by 2 factorial minus t square all cube by 3 factorial plus etc. So this is e raised to minus, which implies integral 0 to z. We want to find the Maclaurin series of this. So integral e raised to z exponential of minus t square dt is equal to integral 0 to z 1 minus t square by 1 factorial plus this you can written as t raised to 4 by 2 factorial minus t raised to 6 by 3 factorial plus etc. Now we will integrate termways. So this is equal to, we will get z, sorry, t minus t cube by 3 1 factorial into 3. Yes. So integral 1 is t. Integral t square is minus t cube by 3 plus integral t raised to 4 is t raised to 5 by 5 into 2 factorial minus etc. 0 to z. If you put the limit, you will get z minus z cube by 3 plus z raised to 5 by 5 into 2 factorial minus etc. So therefore, what is the Maclaurin series? This. So therefore, thus Maclaurin series of integrals 0 to z exponential of minus t square dt is equal to z minus z cube by 3 plus z raised to 5 by 5 into 2 factorial minus etc. Okay. So this is the Maclaurin series. Now we will do a problem in Taylor series, and we will discuss other problems. So I will do this problem. Find the Taylor series with the center z naught and its radius of convergence naught. Okay, so 1 by z, Taylor series of 1 by z with the center z naught is equal to I. So we can do that problem. Find Okay, so the question is, find Taylor series of 1 by z where z naught is equal to I. So the center of the Taylor series we must have I. That means we must have the expansion in the form z minus I. So solution. So we will use the uh, non Taylor series expansion. So we can write this as 1 by z as 1 by z, okay, I plus z minus I, right? 1 by z is I plus z minus I. That is equal to 1 by z. This is equal to 1 by I. If I take I outside, 1 plus z minus I by I. Okay. So this is equal to 1 by I into 1 by 1 plus z minus I by I. So this is of the form, this form is we know that Maclaurin series of 1 by 1 plus z is 1 minus z plus z square minus z cube plus etc. This is valid when mod z less than 1. So we will use this and find out. So there, which implies 1 by z is equal to 1 by I into 1 by 1 plus z minus I by I. this is equal to 1 by I 1. You instead of z, we will use z minus I by I. 1 minus z minus I by I plus z minus I by I all square minus etc. This is valid when mod z minus I by I less than 1. So which implies mod z minus I by mod I less than 1. So therefore this is valid when mod z minus I less than 1. Why? Because mod I equal to 1. Mod I equal to 1. So this the one method is you can use this trick, or other ways what we have to do, we can use the formula. The formula for finding f of z equal to 1 by z, then z naught is equal to I, then we can use the formula f of z is equal to n equal to 0 to infinity f nth derivative at z naught divided by n factorial z minus z naught all power n. So here f of z is equal to 1 by z. Then what is f of I? F of I is 1 by I. So you find out again f dash of z. F dash of z is 1 by z minus 1 by z square. Then f dash of I is minus 1 by I square, which is equal to 1. So similarly, you find out f double dash of z. This is 2 by z cube. Okay. Then f triple dash of z I equal to 2 by I cube, which is equal to 2 by minus I. So and so on, you will get a pattern. Then you use this. So we know that 1 by z Taylor series of 1 by z is f of I by f of I plus f dash of I by 1 factorial z minus I plus f double dash of I by 2 factorial z minus I all square plus etc. So you can substitute here the values 1 by z, 1 by I plus z minus I plus 2 by minus 2 by I z minus I all square. Okay. Okay. And I take hello. Okay. So we can do this manner also. So if you simplify this, then we will get the same answer. So if you simplify this, you will get the same answer what we done here. So that is the method to find out. Now I will give you an hint of other problem, how to do other problems. So if you want to do this problem, Maclaurin series of z plus 2 divided by 1 minus z square. For doing this problem, we will make it into, this is z plus 2 by 1 minus z into 1 plus z. So this can be written as z plus 2 divided. Okay, this can be make into partial fraction a by 1 minus z plus b by 1 plus z. So then you find a and b, then you can use 1 by 1 minus z expansion and 1 by 1 plus z expansion. So for this type of question you have to make it into a partial fraction. Now if this sin square z, for this problem sin square z you can written as 1 minus cos 2z by 2, and you know the expansion of cos z, cos 2z, then we will do the problem. Okay. Similarly here this we can do in the same manner. Here instead of z we can use 3iz. Okay. So similarly we can do all other problems.